we ended the last video on this slide, and we're going to spend this video going over it a little bit more. So by the end of the video, you should understand how this little animation leads to this spectrum that you see over here. So that's our goal in this video. And this unit's kind of a tough one to put into video format, so for the most part, pick up what you can, write it down, bring questions to class, because that's going to be the key to us understanding this. So some terms that you need to know. We're going to go through these quick, so pause the video if you need to write these down. Ground state is the lowest energy form of an atom. So when the electrons are as close to the nucleus as they can be, we call that the ground state. It's the most stable state. The atom is happy in this state. The excited state, or the promoted state, is when the electrons will jump up to higher energy levels. So they're no longer in their lowest possible energy level. So this is not stable. The atom gets very anxious when it's in this state, and so the electrons will eventually fall back down. Now it takes energy to jump up, and it needs to release energy to fall down, which is what we're going to talk about later. So for now, just understand ground state, excited state. And then the Bohr model of the atom is where we're currently at. So this is kind of just a review. We know that the Bohr model looks like this over here. So you got the nucleus in the middle, you got your rings, that the electrons can only travel on these rings. So the electron can be here, here, or here, but it cannot be in the middle. So that's essentially what the Bohr model leads us to understand. The electrons can only be found on certain orbits. Now, the higher the orbital, the greater the energy. So the highest energy orbital is further away from the nucleus. The lowest energy is close, the closest to the nucleus. So the closer you are to the nucleus, the lower energy, because the electron is being pulled in to the positive nucleus, right? The electrons are negative, it's being pulled in. So the closer it is, the lower potential energy. It takes energy to pry the electron away from the nucleus. So think higher potential energy as you move out. Now there's 7 energy levels total. The farther the fall, the greater the energy released. So if I've got an electron here, it can either fall to this energy level, or it could fall to this energy level. If it makes that fall, it's releasing more energy because it's falling further. It has to give up more energy to fall down. So quick review, ground state, the electron is in its... There we go, interrupted by the bell. The ground state is when the electron's at its lowest state. And then if it gains energy and goes up, now we say it's in the excited state. So I got little emoji faces here to remind you. It's happy when it's in the ground state. It is anxious when it is in the excited state. So light as particles. So we talked about in the first video properties of waves, like amplitude, frequency, wavelength. But we find that if we apply only those principles to light, it doesn't explain everything we observe in nature. Well, and if it doesn't explain everything in nature, it's not a very good theory. But we also know that light does act like waves. So it's kind of weird. It acts like waves, but the waves don't explain everything about it. It's an incomplete picture. So scientists also treat light as if it's made of particles. So we're going to start talking about that now. So that includes the quantum concept. So it says some behaviors can't be explained by wave theory. And wave theory works well for continuous spectrums, but it doesn't work well for emission spectrums. It can't explain how do we get this pattern if light only behaves like waves. So we're going to figure out how to explain this, talking about the particle side of light. So we're going to start with a quantum, which is a finite packet of energy that can be gained or lost by an atom. So energy is given off in small specific packets called quanta. So I'm going to just have you write this down for now, go with it. If it doesn't make sense perfectly yet, that's fine. It'll clear up hopefully later in the video. Now there's an equation that was created that says E equals hf, where h is Planck's constant, which is this number. So just ignore that for now. But what it means is that light that has a higher frequency will also have a higher energy. Light that has lower frequency also has lower energy. Now you might have remembered in the video before, we have two waves that look like this. This one has a much bigger amplitude, this one has a much smaller amplitude. And remember, amplitude tells us how much energy a wave has. If you remember, I didn't mention anything about frequency telling us how much energy a wave has. But it turns out that light works like this, and it's a weird concept, and it took a lot of smart people to figure this out. But what it means is that this light naturally has less energy than this light. This light has higher frequency, so it's going to have a higher energy, regardless of the amplitude of each wave. So there is a little bit of a catch there. So we've got this equation. What we're going to look at is the relationship here. The relationship between frequency and energy is that if frequency goes up, so does energy. So higher frequency lights have more energy. So there's a direct relationship here. Now if wavelength goes up, we know that as waves get longer, their frequency goes down. So if this one has a higher frequency, so this has a shorter wavelength, higher frequency, higher energy. This one has a longer wavelength, which means it has a lower frequency, which would mean it has lower energy. So there's an inverse relationship here. Longer wavelengths have lower frequency, which means they have lower energy. Okay, now you need to know these. So you'll have to study these and memorize these for the test. What you need to know is that blue light, you don't need to know the exact values up here, but what you do need to know is that red light has a longer wavelength. So you can start, red light has a longer wavelength, blue light has a shorter wavelength. And we use these two colors because they're the opposite ends of the visible spectrum, the light that we can see. Red is about the longest wavelength we can see, and blue is about the shortest wavelength we can see. I mean, purple's technically a little shorter than blue, but scientists just use blue as the convention. So because red has a higher wavelength, it has a lower frequency. It also has a lower energy. Blue, because it has a lower wavelength, has a higher frequency and a higher energy. So you need to know that blue light has more energy than red light. And that's going to come back in this video. Blue light, higher energy. Blue is better. There you go. Okay, a photon. A photon is an individual quantum of light. So light, you can think of it, it carries packets of energy that it delivers. Different light carries different sized packets, and we're going to come back to that too. So radiation is emitted and absorbed in whole numbers of photons. So this is really important. You can't deliver a half of a photon. You can't deliver multiple you can't deliver 1.5 photons. You can either deliver 1 or 0 photons, or 2 photons, 3, whole numbers only. You can't absorb a part of a photon. It's an all or nothing scenario. So Einstein, in 1905, he proposed that electrons also behave like waves and particles. So we know that light behaves like waves and particles, and now Einstein says that electrons do too. So we're going to get back to that in a little bit, but what I want to draw here is I want to draw say a beam of red light. Red light, remember, has a longer wavelength. Blue light has a shorter wavelength. So let's draw, sorry, my hand is sticking as I draw here, so it's not the smoothest. Okay, so we know that red light has a longer wavelength. So we know that its frequency is lower and it has a lower energy. Blue light has a shorter wavelength, but it has more energy. So here's how I like to think of light. The wave, that seems to make sense to students, right? Let's pretend like they both have the same amplitude, but red is longer, blue is a skinnier wave. but the particle side of light. This is the tricky part. Now here's how I envision it. Red has lower energy, and we think of photons as packets. So what I do is I draw little envelopes. This is how I think of it. Red carries these little packets of energy that it delivers to whatever the light hits. Blue light is shorter, even though it's shorter wavelength, it carries bigger packages of energy. So you can think of blue light delivering these big packets of energy. Red light delivers these little packets. Now it doesn't matter how big the amplitude of this light is. Let's say it was a big amplitude. Red light only carries that big of a packet. This would be a brighter red light, but it doesn't carry any bigger packet. Now blue light, no matter how dim or how bright it is, it always carries this size packet. So keep that in mind. Because what we're going to do is we're going to draw a quick picture here. Here's how this relates to an atom. Then we're going to draw our little spectroscope here. We got our numbers 4, 5, 6, 7 as you look through them. Now imagine I got an electron here. And imagine that I shine some red light onto this electron. And what it does when this light comes in contact with this electron can say, oh, hey, you're delivering me a package. That electron can potentially absorb that energy, or it doesn't absorb it. Now let's say that this package of energy is just enough energy to get the electron to jump to right here. Is the electron going to absorb this packet? The answer is no, because the Bohr model says that the electron can be here or here, but it can't be in the middle. So this electron isn't capable of absorbing this package of energy. So it won't. This light will go right through this atom. It won't interact with that electron. Now let's say that we have a blue light. Let's see, I'm going to see if I can change this here. There we go. Let's say we got a blue light. There we go. Blue light, shorter wavelength. The blue light comes in, it carries a bigger packet of energy. Let's say that if this electron absorbs it, that blue light is the perfect amount to get it to jump to this energy level. If that's the case, then this electron will absorb this packet and it will jump up. Blue light would interact with this electron. Now because the blue light, or the electron absorbs the blue light, it jumps up, we now say that it's in an excited state. And what happens to all electrons in their excited state? They fall back down. So when this electron falls back down, it's going to give off energy. Now that energy was equal to this size packet, right? So the energy that goes in must be the energy that comes out, so we get that same blue light that comes out. Now that blue light, if we're looking at a spectroscope, would show up as like a blue stripe right there, somewhere in our spectroscope. So what we're seeing here, this blue light, is from an electron making this transition, which happens to be the exact transition, just enough energy to be a blue photon, and then it gives off that blue photon of light. If it were to make a bigger jump, that might even be out of the visible range. This might give off UV light, UV, which is even higher energy, which would be out here somewhere where we can't even see it. Let's say that there was a smaller jump. Let's say there's another ring in here. Let's say there's a smaller jump. This might be lower energy, might be about the energy of yellow light or orange light. If this particular atom has a gap that matches orange light's frequency or energy, then you'd see a band right here. And I'm sorry, I'm not going to quick change to orange here. But depending on the size of the jump, that will affect which light that atom absorbs and what light comes out when the atom does fall back down. We'll spend a little more time drawing this and explaining it in class, but at least get the main points of this down and maybe go re-watch this particular section if you need to.